Imagine being able to clear up fuzzy, noisy medical images with a revolutionary method inspired by the strange world of quantum physics. This breakthrough could dramatically improve how doctors interpret ultrasound and MRI scans, which are often clouded by background noise that blurs important details and makes precise diagnosis challenging. But here's where it gets controversial. What if the key to solving one of medical imaging's toughest problems lies not in traditional methods, but in applying the complex mathematics of quantum mechanics directly to the pixels themselves? Medical imaging technologies, like ultrasound and magnetic resonance imaging, MRI, frequently suffer from unwanted noise that distorts the picture. This noise creates a visual haze that obscures tiny structures doctors need to see clearly. For healthcare professionals, removing this noise is crucial for making accurate decisions. While existing denoising techniques have made progress, they often fall short because noise in these images is highly complex and variable. Moreover, most methods require laborious manual tweaking of parameters, which adds to the difficulty and limits automation. In a bold new direction, some scientists have turned to the principles of quantum mechanics, the branch of physics that explains how particles behave at the smallest scales. These researchers spotted a fascinating analogy. Just as particles vibrate and spread out in space, pixel brightness in an image can fluctuate and blur, causing noise. Until recently, no one had successfully taken the full mathematical framework from quantum physics and applied it directly to improve image denoising. A groundbreaking study published in the journal AIP Advances brings this concept to life, led by a team from Massachusetts General Hospital, Harvard Medical School, Weill Cornell Medicine, GE Healthcare, and Université de Toulouse. They advanced the particle-pixel analogy far beyond previous attempts. Quantum localization is a well-known physical phenomenon where particles remain confined within a limited region, explains Amirreza Hashemi, one of the lead authors. Our key innovation was to literally translate this physics concept to how noise behaves in images, not just metaphorically, but by using the actual mathematical description. This fundamental connection hadn't been formalized before, and to our knowledge, we are the first to do so. Localization in physics describes how vibrations or movements can either stay concentrated, localized, or spread out, diffuse. Think of vibrations in a solid material. If they remain restricted to a specific area, they are localized. If they spread freely, they are diffusive. The researchers realized that pixel intensity in a clean image behaves like vibration confined to a spot, localized, whereas noise causes the pixel brightness to scatter widely, essentially diffusing. By applying the same quantum mathematical descriptions that govern particle vibrations in physical space, the team developed a way to differentiate between true image signal, localized pixel intensity, and noise, diffused pixel intensity, in medical images. This separation allows for the extraction of crisp anatomical structures without the interference of random noisy pixels. The heart of our approach was designing an algorithm that automatically distinguishes between localized signal components and diffused noise components in an image based on their unique behaviors, Hashemi notes. This physics-driven approach is particularly powerful because it removes the need for manually adjusting parameters, a major bottleneck in traditional denoising techniques. Our method leverages fundamental physical principles like localization and diffusion dynamics to inherently separate noise from meaningful signals, Hashemi adds. This means the algorithm naturally works as intended, without requiring expensive brute force optimization or tweaking. Beyond medical imaging, this novel approach hints at exciting possibilities in quantum computing as well. Because the algorithm aligns with how quantum computers operate on physical principles, it could one day help quantum systems process information more efficiently as they scale up. Our physics-based framework harmonizes beautifully with the computational building blocks of quantum technologies, Hashemi says, potentially offering advantages as quantum computing evolves. But here's the part most people miss. This work challenges the accepted boundaries between disciplines. Applying quantum physics directly to image processing is unconventional, and it raises important questions. Could this truly reshape the future of medical diagnostics, or might the complexities of quantum math limit practical adoption? What trade-offs exist between this sophisticated, physics-inspired approach and traditional machine learning denoising methods that are now widespread? We'd love to hear your thoughts. Does the idea of using quantum principles to improve everyday medical imaging excite you? Or does it seem too abstract and complicated? Could this be the breakthrough in clarity clinicians desperately need, or just a theoretical curiosity? Join the conversation and share your views below.